Welcome to the video for Lecture 19, Section 2. This video continues the fluid heater problem. In the previous video, we found all of the transfer functions and developed the closed-loop feedback control block diagram. For this video, we will develop the overall transfer function for a water heater for both the servo and regulator problems and find the time-dependent response using the data given for the water heater problem. Here is the block diagram with all the transfer functions we found in the previous video. We are now ready to find the overall transfer function. Our task is to find the transfer functions for both the regulator and the servo problem. Here is the transfer function for the servo problem. To put it into a form with which we can get the coefficients we need for using the MATLAB residue command, we need to multiply the numerator and denominator by the two terms tau p times s plus 1 and tau m times s plus 1. Then we need to multiply out the terms in the denominator to get the s squared term and the s term. In this case, the s squared term is tau p times tau m, and the s term is tau p plus tau m. Here's the block diagram for the overall transfer function for the servo problem when the set point changes. Here's the overall transfer function when the load changes. This is the regulator problem. Again, to simplify it and put it into a form to get the coefficients we need to use the MATLAB residue command, we need to multiply the numerator and denominator by tau p times s plus 1 and tau m times s plus 1. Here's the block diagram for the overall transfer function for the regulator problem when the load changes. In this case, the load change is when the inlet fluid temperature Ti changes. Here is the overall transfer function for the combined servo and regulator problem. Now both the set point and the inlet fluid temperature can change. The equation can be reorganized to pull out the common terms. For our servo problem, we will assume that the set point has changed by a step change of magnitude minus 10 degrees. The transfer function for Tr is minus 10 over s. Now we can substitute minus 10 over s for Tr in our servo problem transfer function. The course packet lists the other data we need. After we insert all the values, we get the servo problem transfer function shown. We can use the MATLAB residue command to find the coefficients and roots to write the partial fraction expansion of the expression. Here is the partial fraction expansion. We take the inverse using equations 3, 15, and 6. We then can write the time domain expression for the problem. This describes the water heater temperature for a 1.2 cubic meter tank with a 0.01 cubic meter per second flow rate that is using proportional control when the set point temperature is reduced by 10 degrees. Here is a plot of the servo set point change process response. This plot neglects the steady state outlet fluid temperature, so the ideal response would be to have a zero output. Notice that the long-term response has an offset of about 9 degrees. That is because we are using proportional control alone. These are the partial fraction expansion and time domain temperature response equations for a step change to an inlet fluid temperature of plus 5 degrees. The transfer function for Ti is 5 over s. Again, we need to substitute 5 over s into the regulator transfer function and find the coefficients that we can use the MATLAB residue command to find the coefficients and roots to write the partial fraction expansion of the expression. Here is the partial fraction expansion, which can be inverted using equations 3, 15, and 6. The time domain expression is shown at the bottom of the slide. Here is a graph of the regulator problem response to a plus 5 degree step change in the inlet fluid temperature. The long-term response is about 4.5 degrees. The offset remains because we are using proportional control only. Here is a graph with the servo response, the regulator response, and the combined response to the combined step change in the set point and inlet fluid temperature. One more time, let me remind you that you will not need to develop the transfer functions from initial ordinary differential equations. You can use the transfer functions we've developed that are in the course packet. This brings me to the end of the Lecture 19 Section 2 video. Write down any questions you have and bring them up in class or lab.